First, we're going to establish why documentation is important. Documentation is necessary to identify the purpose of the software and its requirements. Note that I mentioned it's going to identify the requirements as well. So for instance, I work at Sandia National Labs on a piece of software called Trilinos. And recently, Trilinos added a requirement on C++11. So now the documentation states you have to have C++11. If you don't note such things in the documentation, then you get a whole bunch of errors from the users saying, I can't compile your thing, why can't I compile your thing? So it's necessary to say these are the requirements of the code. Documentation clarifies what each component of the code does, what's needed to maintain it, and how it can be reused elsewhere. The main purpose that most people think of when they think of documentation is providing user support. I recognize some of the names in this room from the Trilinos user list, the list of people that email the developers at Sandia. I love answering questions about Trilinos. I especially love answering questions about the eigensolver package because I don't get to talk about eigensolvers nearly enough in my life. But I also have to do other things at Sandia apart from answer those emails. We have documentation that answers a lot of questions, and maybe people just don't notice the documentation sometimes. They might not see that we documented a particular abstract interface. So they send an email to the list, and then instead of writing an email that takes an hour every single time that same question is asked, we refer them to that place in the documentation. Documentation is also important to ensure that software is used within its region of validity. And by that, I mean to make sure that the software is only used to solve the types of problems that it should be able to solve. I wrote an eigensolver for Trilinos a couple years ago. And I know I keep mentioning Trilinos. I will define what Trilinos is in a couple slides. I wrote an eigensolver for Trilinos a couple of years ago. And that particular eigensolver has some constraints. It only works on symmetric eigenvalue problems. It is only guaranteed to converge to extreme eigenpairs. Will it converge to interior ones? Yes, sometimes, but it's not guaranteed. So if I had never documented that particular, if I had never documented those requirements of the code, and then somebody took that code and ran it on a non-symmetric problem and got a result and published that result, that would be really, really bad. Because their result would almost certainly be wrong. And it would make them look bad for publishing a bad result. It would make me look bad because I wrote the code. It would make my advisor look bad because he came up with that algorithm. It would make Sandia look bad. So you need to make sure that software is documented so that people don't misuse it and then publish it and produce spurious scientific results. There are several different categories of documentation. First of all, there's the user guide, which most people think of when they think of documentation. It tells the user how to use the code. There is also a reference manual, which lists the interfaces and routines and explains their functionality. This might be a little more useful for developers who are working on the project. This type of documentation can be generated automatically from the code, and that's what we'll be spending most of our session talking about today. Readme files are generally shorter pieces of documentation that might just live in the code repository. Installation guides are necessary for codes where installation is non-trivial. So for PETC, which I believe you talked about last week, for PETC, there's this beautiful installation guide online. Trilinos, we also have a user installation guide because we use CMake, and CMake isn't necessarily the most intuitive thing in the world. The last category of documentation that a lot of people overlook is tutorials. Tutorials are a form of documentation. So what I'm getting at with this slide is that all software needs to be documented for the reasons listed on the previous slide, but not all software needs a user's guide. The type of documentation that your code needs is going to be based on how many developers you have, what the code is used for, who the code is going to be used by. So Trilinos. I'm a postdoc at Sandia. This is what I work on. Trilinos is kind of my entire universe. So I'll be talking about how Trilinos tests and documents the code, or how we test and document Trilinos. Trilinos is a collection of libraries intended to be used as building blocks for the development of scientific applications. That came from the Wikipedia page. What I usually define Trilinos as is Sandia's big calculator. Argonne produces PETC. Trilinos is very, very similar to PETC. It has different functionality. It's written in a different language, but they're fairly similar packages. Trilinos is organized into 66 different parts. In Trilinos, we have linear solvers, both direct and iterative. We have nonlinear solvers, eigensolvers, preconditioners, algebraic multigrid, optimization packages, time integration, and really, really cool stuff. As to the scale of Trilinos, it has over 10,000 commits, and I think it has dramatically over 10,000 commits. According to GitHub, it has 135 contributors, so this is not some piece of code that 3 people are working on in a tiny little office. And it has millions of lines of code. So how do we handle documentation at Sandia? Each of these packages is handled differently. Some of them have user manuals, like Mulu, the algebraic multigrid package, has a beautiful user manual. So does Aztec.oo, the Krylov solver package. Tefos RCP is this tiny little piece of one of the packages, and it has its own 40-page manual, I think. We also have publicly available tutorials, presentations, and slides. There's been a Cocos tutorial at Supercomputing for the last couple years, and that's available up on GitHub, and it's amazing. tpetra also has publicly available tutorials. Most of our packages also have well-commented examples, which a lot of the users like. A lot of our users like to download the code, be able to modify a couple things in one of our examples, and then run the problem that they want to run. They don't want to read an entire manual, they just want to be able to take the code and use it. We also have automatically generated HTML documentation, which is what the rest of this talk will be about. The automatically generated documentation was generated using Doxygen. Doxygen is one approach to producing reference manual-like documentation, and it automatically generates HTML or LaTeX documentation from the comments in your source code. What I really like about Doxygen is that it's easy to update the documentation when the source code gets updated, so you can keep them in sync. For instance, I had a piece of code that recently I was modifying. I was storing a particular quantity as an integer, and it turned out that the things we were storing, there could be more than 2 billion of them. So shouldn't be stored as an integer. So I had to update the code and use a size t instead of that. If I had had a user manual that I wrote by hand from scratch, then I would also, when I updated the code to use a size t, I would need to update the documentation to say this thing now uses a size t. But because I was using Doxygen, that change was automatically propagated over to the HTML files. So Doxygen, the command, takes what's called a Doxy file as its input, and you can generate this by hand. What's contained in it is information like, this is where my source code lives, these are the types of files I would like you to process, you should ignore these things, this is where I would like the HTML files to live. I don't personally like writing the Doxy file from scratch, so I tend to use Doxy Wizard, which is a GUI front end for Doxygen. And it generates the Doxy file for you. So now we're going to do a small Doxygen demo. And in this demo, we will be using a small linear algebra package called Morpheus, and it's available at the website listed there. It is a small linear algebra package specifically generated for this tutorial. We will also be using it for the testing session later this evening. So it has bugs. It purposefully has bugs. Please don't actually try to do science with this code. OK, so Morpheus contains a matrix class and a vector class. We're going to be documenting the vector class in this tutorial. OK, so here's what the Doxy Wizard looks like. And I apologize for the font size. I can't do anything about that. I can't make it bigger. So I'll narrate to you what I'm doing. The Doxygen GUI front end specifies exactly what it wants you to do. So it says here, step 1, specify the working directory from which Doxygen will run. So we're going to tell it, this is where my code lives. My code is living in this directory here. Step 2, configure Doxygen using the wizard and/or expert tab. Then switch to the run tab to generate the documentation. OK, so here it asks for some pretty basic information. What is the name of your project? And I'm going to call it Morpheus, because it's about matrices. That reference would have made a little more sense back in 1999 or so. OK, and we specify the directory where it's going to look for the source code. You guys got it now. OK, So we specified where the source code lives, and we're going to specify a directory where Doxygen is going to put the documentation. I'll make a new directory for it. I'll call it Doxy Files. And you know what? I'm not going to touch any of the other options right now. I'm just going to run it. So when we switch over to the Run tab, there's this button here that says Run Doxygen. You click that. It says it's currently running. And it outputs a lot of information here that you can't read because the font is too small. But what it says is, I'm processing these files that live in this directory. And it spit out some warnings because the vector class was not documented. At the bottom, there's a button that says Show HTML Output. We can click on that to see the output of Doxygen. OK, so this is a little anticlimactic. We get this blank page that says, this is the Morpheus documentation. But we see some other tabs. And up at the top, there's a tab called Classes, so I'll click on that. There we go. And we see Vector down here. Vector has absolutely nothing next to it because we didn't document it yet. If we click on Vector, it pulls up all of the public member functions of that class. And none of those are documented either. But we see that it did at least pull out, these are what the operations are. We're going to add some comments to the code. This is our code for the vector class. And as you see, it has absolutely no comments in it right now. To make a Doxygen comment, you use your regular C++ style comment, but you add an extra asterisk. And that signals to Doxygen, this is a comment that you should process. If you have a comment that looks like this, Doxygen will not process it. So the comment to create a main page is /main page. And then I'll give it a title like Welcome to Morpheus. And I'll add an exclamation point because I'm very excited about this project. And then we can have some text underneath. And now if we try running Doxygen again, we're going to get a different result. So now we see that instead of that blank, disappointing looking page from before, we now have a title, Welcome to Morpheus, and there's some text below. And if we wanted to, we could create different sections. We could put all kinds of stuff there. But I'm not going to demo that right now. We're going to work on our vector class and documenting that. So now that you've seen a little bit of Doxygen, what do you think the command is to document a class? Wild guess. What are we going to use to document a class? /class. And then below it, we're going to put a brief description, signaled by the word brief. And I'll say it's a dense vector class. And if we run Doxygen again, Doxygen is going to pick up that comment. And we now see that vector is a dense vector class. So we're going to go through and comment a couple of these functions. I'm going to start with this one. This is our constructor. And as before, I'm defining a brief summary of what this function is. If we skip a line, then we can also specify a longer description of what this particular function does. And I'm going to say it allocates memory for a vector. I'm I'm also going to put a special note in there because I personally like to note in my code where I allocate and deallocate memory so that I can keep track and make sure there are no memory leaks. How do you think we define a note? /note. You got it right. I don't know if that was a guess, but that's the correct answer. Note. I'm going to note that the size of the vector is constant and can't be changed after construction. And you know what else? I'm going to make a to-do item to signal to myself for later that I want to be able to resize this thing that we can't currently resize. How do you think I define a to-do item? /to-do. This barely even needs a tutorial, right? And we'll run our Doxygen again. And it's still complaining about all of the functions. I know you guys can't read it. Those complaints there, they're about the functions that we didn't comment. And it's saying, psst, you didn't comment this function. You should probably comment that function. So we're going to look at the HTML output again. And if we go to vector this time, we see the constructor is now commented. That is the brief description. And if we select more, we see the full description. So we see the special note that we put there. I think you can also define warnings. For instance, if you've deprecated a function and you want to warn somebody, hey, you're using something that you shouldn't be using, you can say I can't remember if it's /warn or /warning. And there's a to-do item here. One cool thing about Doxygen is I can click on this to-do, and it will pull up my entire to-do list from all of those different files. So I also decided earlier that I wanted to add some things to Matrix, and it put all of those things that I said I wanted to do later in one little place. One last thing that I'm going to show you guys that's another cool feature of Doxygen. We're going to move to the dot product function. You can have equations in Doxygen the same way that you can in LaTeX, but the command is a little bit different. I believe it's -f*. And if I'm right, we're going to get a function. Or we're going to get some an equation. Wrong one. There we go. OK, so it understood that LaTeX code that we put in there. It was able to parse this x transposed x here and render it correctly. So at this point, I've shown you all the features that I wanted to show you from Doxygen. Are there any questions about it? Yeah. Absolutely. OK, let's do it. How do you guys think that we document parameters? /param. And we can say that this is an input parameter or an output parameter. I'm going to say that this one is an input parameter because we see it's a const reference. It's called B. And I'll say OK, so this is the command to define a parameter. And now we're going to render it. There you go. That's a parameter. There's also a /return that does exactly what you'd expect it to do.
In the LaTeX command you showed, we're replacing the $sign with a /f$.
Yes.
The only change you need to make when you're writing the LaTeX part?
It doesn't like certain LaTeX packages, so it gets a little funny about arrays, I think. But there is a way to make it recognize arrays.
But
But for the most part, yeah.
This just the -f we need to remember. Oh, that's great. Thanks.
I guess yes, but can you include figures or external objects like videos or?
You can absolutely include external objects. Right, I didn't show you guys this. So on my slides, I pointed to a particular GitHub address, and we're going to go there right now. So at that GitHub address, I put some fully commented files for Doxygen. So if we scroll down to please see this page and click on that, this is a page that was generated entirely by Doxygen. And if I had continued commenting the vector code, this is what we would have ended up with. So you can see here that I have a link to a LaTeX manual here, a link to a PDF. And you can open that like you would anything else. I don't know much about embedding videos and whatnot, but I assume it's about the same.